So you want to build your own everything remote? You're in the right place. This guide is a companion to the video where I show you the remote in use and talk you through a bit of the design process. If you haven't seen it yet, I'd recommend watching that first. It'll give you a better sense of the design decisions and what the everything remote actually is capable of. There's a link to the video in the description. This video will go in depth on how to build your own one of these remotes. It's by no means exhaustive, but you should be able to stumble your way through without any real experience. This tutorial is here to help you actually build the thing, so I've broken it down into a few chapters. You can skip around using the bookmarks in the description below. Chapter 1 is what you need: tools, parts, 3D printing files, that sort of thing. Number 2 is 3D printing, how to set up and print all the parts. 3 is electronics, which is assembling and soldering your custom PCB. 4 is assembly, which is pretty self-explanatory. 5 is your software, programming your ESP32 with ESP Home. And 6 is your automations, using the remote with Home Assistant. Whether you want a media remote, a smart light controller, or something totally custom, this should give you everything you need to make it happen. Let's get started. The first thing you'll need to do is visit the blog post linked in the description and make sure you have everything in the bill of materials. I've also included links so you can just pick them up from the same sources I used. If you've got everything, you should have your PCB, your ESP32 dev board, 21 tactile switches, 2 10 kilo ohm resistors, 2 10mm M2 screws and 3 8mm M2 screws, your LiPo battery cell, and some double-sided tape to hold it in place. You'll also need some tools, including wire cutters or flush snips, some tweezers, solder, a sponge or brass wool for cleaning your soldering iron, some blue tack, and of course, a soldering iron. A multimeter is also a great idea if you have one and know how to use it, but it's not absolutely necessary. If you're new to soldering, I recommend a TS80P for your first iron. You should also have everything you need to 3D print the enclosure. We'll go through how to print the components and customize your icons first, so you can have your prints going while we work on the electronics. Again, all of these items are available in an easy to read list in the blog post below. Alright, let's talk about how to actually print the enclosure and the buttons for the remote, whether you're using the versions I've designed with built-in icons, or you're planning to add your own. We'll walk through everything you need to know, including materials, orientation, painting icons in Bamboo Studio, and even how to add your own custom SVGs if you want to go full DIY with the layout. I'll show you how to do this in Bamboo Studio because a lot of you are likely using that slicer, but the same principles all apply in Cura, Prusa Slicer, or your slicer of choice. Let's start with the files. There are 3 main versions you'll find on printables, link in the description and on the blog post. The one you've seen in the video, that's the labeled version with icons already built in. A blank version with the same enclosure and button layout, but with no icons, so you can customize it however you'd like. And third, a no button step file. Just the shell, no buttons at all. That one's for anyone who wants to go full custom in Fusion 360 or another CAD tool using this PCB, but their own button layout. I've also included a 3D model of the PCB layout so you can see where all the tactile switches go. Super handy if you are doing your own layout. I printed the whole thing in PLA. It's easy, reliable, and works well for this kind of detail level. I did test a few alternate builds in PETG, which also works great, but is a bit more prone to stringing, especially if you haven't dried it properly. So just keep that in mind if you're going for a clean multi-material print. For the colors, I went with a light gray for the button bodies and a black for the icons. I'd recommend sticking with high contrast colors. It makes the icons easy to see and makes the detail look a lot sharper, which is helpful when they're this small. Now I'll show you how to set up your buttons and shell in Bamboo Slicer for printing. If you're using the labeled button models I've included, the ones with the icons already built in, the process is fairly straightforward. The icons are embossed into the surface of the buttons about 0.5 mm deep. All we need to do is add a filament change at the layer that corresponds to when the printer will bridge over the gaps left by our icons. It'll all make a bit more sense once we get there. I've already downloaded the models from Printables, so the first thing we need to do is import all of our models. So we'll grab the icons, buttons with icons, the shell bottom and the shell top files, and import them all. We're just going to select no here to tell Bamboo Slicer that they're all separate parts. There we go. Now I'm going to add a couple more plates for my back and front shell. And the shells both print with the outside down. So we'll just reorient the prints using the lay on face command or lay on face tool. Okay, we'll come back to the shell later. We'll set up all the buttons first. First thing we need to do is move the select button out of the center of the directional pad. Then we'll select all of our buttons and choose the filament we'd like to use. You can use this object selector on the left-hand side to do this. Now all the buttons have this flange here that we need to support while printing. So we're going to work our way through all of our buttons and paint on supports. We can't rely on the slicer to auto support all the right areas because it will support the inside of our embossed icons, which we obviously don't want. So instead, we're going to use the support painting tool up the top here, or with the shortcut key L. We're going to select fill mode and we're going to select on overhangs only. This will allow us to really easily paint the supports without having to sort of manually make sure we get everything. So we're just going to work our way through one button at a time, clicking on the area we need supported, which is this flange, and then moving to the next button. Okay, now we've painted all our supports. We can close the support painting tool. Just a quick note, if you do mess up on any of the buttons and maybe select the wrong surface, you can just hit erase all painting while you have that particular button selected. It'll only erase the painting from the one currently open, not all of them. So you won't have to start over again. So we'll close the painting tool. Next, we need to tell Bamboo Slicer what kind of supports we'd like. So we're going to select all of our buttons, go to the support section of your print settings, enable support, then we're going to select normal manual. What that means is it's not going to try and place any supports by itself. Instead, we're telling it to only place supports where we've put support enforcers or painted support enforcement. Then we're going to select snug for the style and on build plate only. Now, if we slice our buttons, you'll see the slicer has generated all of our supports. Now, I have found that sometimes Bamboo Slicer will add a brim, which isn't necessary with the supports here. So I just like to set it to no brim to make sure it's not doing that by accident. Okay, that's all our buttons. Now you could print them like that. I don't like to print them so close together just because it tends to result in more failures for me. So I'm just going to hit arrange on this particular plate to lay them all out a little wider, and we'll slice again. Great. Now we need to add our color change, which will be what makes our icons visible. If we grab this handle at the top here and scroll down by layer, we can see that while the printer is printing the first few layers, it will leave these areas empty, which is what we want. What we're going to do is on the layer where there is a change or where we start bridging over the gaps left previously, we're going to add a filament change. So scroll until you find that point. In my case, this will depend on your slicer settings and your layer height settings, but at layer 0.58 millimeters is the height at which it starts bridging. we're going to right click on that little plus sign. We're going to hit change filament and select our other color. In my case, it's just other gray. And there we go. So now you can see the color has changed in this bar on the right. We're going to hit slice plate again and drag the bar up. And now you can see that those icons are filled with a different color. Why do this instead of just printing the icon in a different color on the same layer? I found the tactile feedback really helpful while using the remote. It's a little easier to feel where the button is. And the end result, I think, looks a lot sharper in my testing, which is really important when the icons are so small. It also means you can use any printer on it because you can even do a manual filament change to swap over. So that's the buttons sliced. The front and the back are dead simple to set up. You can print them on separate plates if they're different colors to avoid having to do any filament changing at all, which is what I opt to do. You can just use a 0.4 mil nozzle for these if you want to speed things up a little bit. For print settings on the buttons, I went with a 0.12 millimeter layer height on a 0.2 millimeter nozzle. The only change I made to the default profile in Bamboo Slicer is I slowed down the first couple of layers. So I changed the initial layer to 20 millimeters a second and the initial layer infill to 40 millimeters a second. For the shell, use whatever layer height you'd like. I'd suggest setting the order of your walls to outer, inner. What that means is it'll print the outside wall before the inside wall and generally leads to a better finish on the outside on thin-walled objects like this controller. I use the textured build plates almost exclusively because I like the finish they give, but you should be able to make it work with any build plate. If you have any adhesion issues with the buttons, which can be a little bit of a challenge because of their size, then a bit of glue stick and then isopropyl alcohol over your build plate before you print them can be incredibly helpful. Now, if you're using the blank button models and want to add your own icons, here's how to do that using just SVG files from the internet. You will need an SVG icon for each button you want to change. You can grab them from places like Material Icons, Font Awesome, or just Google whatever you're after with SVG on the end. Just make sure they're clean vector shapes, nothing too complex because the printer might struggle with it. Once you've got your icons ready, right-click on the button you want to customize and choose Add Modifier, then Add SVG. Select your SVG file, and it'll pop up on the print bed. I find it easier with the buttons to look at it from underneath. Now you can drag it around and position it wherever you'd like. You can rotate, you can resize, or you can mirror it if you'd like as well, using the controls just here. Once it's in position, just click out of that menu, head to the Objects panel, select your new modifier, and click Change Filament and whatever color you'd like your icon to be. Now, when we slice the plate, we can see our icon embedded in the button, slightly off center in this case. Now you'll notice that it prints this new icon all the way through the button. This means we'd be doing a lot of unnecessary filament changes. So what we can do to fix this is we can right click on our modifier. We'll go back to the Prepare tab, right click, Edit SVG, and we'll set the depth to something like 0.5 millimeter. You'll need to right click and change filament to whatever you'd like your icon color to be one more time. Then slice your plate and you should see your icon only 0.5 millimeter thick. We scroll down through the layers, we can see that it stops after a handful of layers. You can repeat this process for as many buttons as you'd like. Well, that's the 3D printing side done. Now it's time to get on with our electronics. This is where we're going to take that lovely blank PCB and bring it to life by soldering on all the components. If this is your first time soldering, that's great. This is an excellent beginner project. It's all through hole, which is the easiest kind. No tiny surface mount components, no microscope needed, just a basic soldering iron and a bit of patience and practice. Just a refresher, you'll need some snips, a pair of tweezers, some wire strippers, some solder. I use flux core 6040, it's a really good place to start. Some brass wool or a damp sponge for cleaning up your soldering iron's tip, and some blue tack or something similar to hold everything in place. I'm using the TS80P soldering iron for this. It's a USB-C power delivery iron that runs off a wall plug or power bank. I've recommended it in the blog post that goes along with this project. I'm using it here to show that even something entry-level and portable like this is more than enough for a project like this one and almost any hobby project. If you've already got a soldering iron, great, but I just want to show you don't need anything special to get started. On the board, we'll be soldering 21 tactile switches, 2 10 kilo ohm resistors, one ESP32 microcontroller board, your LiPo battery cell, and of course your PCB from today's sponsor, PCBWay. PCBWay has been my go-to for PCB production for years now, and for good reason. Their service makes it easy to upload your manufacturing files, choose your specs, and have your custom PCB design delivered to your doorstep in just a handful of days. They also offer PCB assembly services. No microscopes or solder masks needed. On top of that, PCBWay provides CNC machining and 3D printing solutions. Whether your home printer can't handle a tricky design or you need something printed in a professional material like PA12, they've got you covered. And it all ships directly to you. From 3D printed stainless steel and titanium to CNC machined aluminium, they can handle high-end materials with tight turnaround times, all at really reasonable prices. It's an excellent way to take your projects to the next level without sinking huge money into your own equipment. You can prototype at home using 3D printing and then send your design off for professional machining when it's ready. Plus, thanks to the PCBWay community, you can buy designs from other makers right on their platform, including the PCB from this project, and support the creator along the way. Thanks heaps to PCBWay for sponsoring this video. We'll go in that order, switches first, then resistors, and then the microcontroller. A really quick soldering primer. If you've never soldered before, here's the quick version. Soldering is kind of like using metal glue. You heat up the joint, which means both the component leg and the pad on the board, and feed in a little bit of solder. It'll melt, flowing into the joint, and then cool into a solid connection that holds everything in place and conducts electricity. If your iron's adjustable, set it to about 320 degrees Celsius and please ensure you have plenty of ventilation. Solder and flux fumes are not good for your health. For each joint, you'll need to touch the tip of the iron to both the leg and the pad at the same time. Hold it there for about 2 seconds. You don't want to get everything too hot. Then feed in just a little solder. It should melt, flow around the leg, and settle into a neat little cone shape. Remove the solder and then the iron. If you need to add any more to make that neat cone shape, you can do that as well. If you add too much and end up with a bit of a blob or bulge, no stress, it happens. Just clean the tip of your iron off with some brass wool or a damp sponge, and then use the iron to reheat the joint, and some of that excess solder will flow onto your tip. Clean the tip again and then carry on. Also, don't feel like you have to get everything right on your first try. These PCBs are pretty cheap and the tactile switches and resistors are dirt cheap. If you're feeling unsure, it's totally reasonable to grab an extra board and a few extra bits and just practice a little bit before starting on your real build. Honestly, I still do that sometimes if something is going to be fiddly, even with years of soldering experience. I've included some links to more comprehensive soldering tutorials below if you'd like to dive a little deeper and build some more confidence. But most of soldering just comes with practice, so you can always just dive in and figure it out as you go. Let's start with the tactile switches, the little clicky buttons that make up the remote. There are 21 of them, and they all install the same way. Line up the legs with the holes in the PCB and press them gently into place. They should sit flat. You don't have to worry about installing them the right way around. They'll work in either orientation they'll fit in. You'll hear a little click as they snap in. That's a good sign. Once they're all in, flip the board over. If you don't have a clamp or vise, don't worry, just a bit of blue tack on both ends will wedge the board in place on your desk or workbench. Each switch has 4 legs to solder. Just work through them one at a time, nice and slow and steady. Again, this doesn't need to be fast. Take breaks, check your joints as you go. You've got this. Next, we'll solder the two 10 kilo ohm resistors. These are called pull-up resistors, and they help the ESP32 reliably detect whether a button is being pressed or not. Here's what's happening. When you press a button on your remote, it connects that pin to ground, which is essentially 0 volts. The ESP32 sees that as a low signal. But when the button isn't pressed, the pin isn't connected to anything. It's just floating. Not high, not low, just sort of undefined. And that can cause weird behavior like phantom button presses. To prevent that, we use a pull-up resistor. It gently connects that pin to 3.3 volts, which is the ESP32's high level. So now, when the button isn't being pressed, the pin is pulled up to 3.3 volts. And when the button is pressed, it overrides that and pulls the signal down to 0 or ground. The ESP32 gets a really clean high or low reading. We only need 2 of these because our microcontroller has some handy built-in pull-up resistors on most of the pins. Only 2 of the GPIO pins we're using don't have them available, so we're adding external pull-ups for those ones. To install the resistors, bend the legs into a U shape and push them through the matching holes. They're labeled on the PCB. It doesn't matter which way they go in, they work in both polarities. Flip the board over and solder each leg in place. I find it helpful once I've poked them through the PCB to put a little bend on the leg where it comes through just to make sure it stays there. Once they're soldered, snip off the excess length of the legs using your snips or flush cutters. Now we're going to move on to the ESP32. Before we do that, we have to make a small modification to the board itself. This particular ESP has this bulky connector on the board that we need to get rid of to maintain our nice slim remote profile. The connector has 4 pins. 2 of them are used to mechanically hold down the connector. The other 2 are our positive and our negative wires. In my testing, I found the easiest way to remove the connector is to take a pair of snips and slowly cut away all the plastic. Take your time and make sure you're only cutting the plastic part. The pads on the board are really fragile, and if you're not careful, you could tear them off the board by pulling on the pins. Make sure not to pull up on the pins at all, cut around them. The plastic will fall away once you've removed enough. Eventually, you'll be left with these 2 tiny pins that used to be inside the connector and the 2 pads that made up the mechanical connection. We'll take our iron and heat each of the pads the pins are on, and then feed in a little more solder. Then we can use our tweezers to pull them off if they don't fall off by themselves. Might be a good idea to warm up the pad and feed in just a little more solder so it's got a nice neat blob on it for you. We'll solder our battery wires directly to these pads a little later, but for now we'll move on to mounting our ESP. Insert the short side of the header pins that came with your ESP module into the top of the ESP PCB. the same side you just removed the battery connector from. While holding them in the ESP, push the long end of the pins through the PCB. Doing both of these at the same time will ensure you don't have any misalignment later. Make sure the headers are sitting flat on both boards and hold both parts in place with some blobs of blue tack. Solder one pin on top and bottom per header strip. This will allow us to remelt the solder and correct any slight issues before we do the rest. Take off your blue tack and check that the headers are still flat to the board on both sides. If they're not, it's an easy fix. Just reheat each of your joints one by one while squeezing the ESP and your PCB together until the gap is taken up. Once you're happy, solder the rest of the pins one by one, working your way from one end to the other. And make sure not to heat one pin for a super long time. If you're struggling to make the joint, move on to another and give it a chance to cool before coming back to it. And make sure you're heating both the pad and the leg. Once you're done, go back and carefully check there's no bridged pins. Bridging is when there's two neighboring pins joined by their solder blobs. This is common if you put a little too much solder into the joint. If there is any bridges, just clean off your tip and use the iron to sort of remove the excess solder until the pins are no longer bridged. Once you're happy, use your snips to cut off the excess length. Use your snips to cut off excess length on the pins on top. That's it. Just take your time and double check everything as you go. You'll do great. At this point, your board should have 21 tactile switches soldered, 2 resistors neatly in place, and your ESP32 mounted upside down on your PCB. Give everything a once-over, look for any missing joints, any solder blobs, or pins that didn't quite get enough heat. If you've got a multimeter, now's a great time to check for shorts between 3.3 volts and ground, just as a sanity check before powering it up. If you're confident everything's been soldered correctly, you don't need to do this. You can also use this opportunity to clean up your PCB with a little isopropyl alcohol and an old toothbrush. That residue you're seeing is excess flux that's come from your solder. You don't need to, but if you want it to look nice and neat, go for it. The last step is to solder the battery to the battery pads. You can run your ESP off the USB-C port if you'd like to get it set up and working before assembly, but I'll leave this up to you. The ESP board we're using has built-in charging circuits, so you can just plug it in with USB-C to charge the battery once it's installed. Just a gentle reminder, LiPo batteries can be dangerous if shorted or damaged. Be gentle, take your time, and if anything feels off, stop and double check before turning it on. To solder the battery, cut the connector off the battery. Be sure to only cut one wire at a time. If we cut them both, we'll be shorting the battery through our cutters, and it could puff up and catch fire. Now we're going to strip the black, negative wire, but not the positive. This will make sure we can't accidentally short the battery by touching our two stripped wires to one another. Twist the loose copper strands together and tin them. Tinning refers to the process of joining the loose copper strands into one cohesive wire with solder. Tack your wire down with some blue tack on the bench and heat the twisted copper strands with your iron, feeding in just a little bit of solder until you can see the exposed copper is saturated. Take your tinned copper wire and trim the tinned end to be only a few millimeters long. You don't want too much excess running the risk of shorting something. Add some extra solder to the pad without the plus sign, which indicates a negative or ground. Lay your tinned wire on top of the negative pad and heat them both to melt the solder. Remove the iron and you should have a nice strong joint. You should have an easier time than I did with this. I felt like a bit of a contortionist trying to make sure the camera could see the joint I was soldering. Repeat these steps for the positive wire, being careful not to bridge the contacts. I'd suggest using a little blob of hot glue if you have a hot glue gun to double check your power wires aren't going anywhere. Those pads can be very fragile and we don't want to tear them off the board. You're done. That's it. The electronics are done. And seriously, if this was your first time soldering, huge congratulations. You've just built a real working circuit board, and that's a massive win. Now we've got our PCB and our 3D prints, we can put the whole thing together. You should have some double-sided tape, 2 M2x10 and 3 M2x8 screws, your PCB, your top and bottom shell, a rag to make sure you don't damage your remote while working on it, and your buttons. Spend some time removing supports and any strings or irregularities in your parts, especially in the button holes. They might stop the buttons from actuating properly. Place the faceplate down on a soft rag or towel and insert your printed buttons one at a time, being careful to fit them the right way around. And then pop your faceplate aside for the moment. Take the bottom half of your shell and put some double-sided tape in the battery compartment and stick your battery cell in place. If you bought the cell recommended in the BOM, it should fit perfectly. Next, put the PCB in the bottom shell and screw it into place using your 3 M2x8 screws. You'll be cutting the threads with your screw as you go, so be careful not to over-tighten and strip out your threads. Once your PCB is securely mounted with the battery underneath, it's time to fit the two halves together and finish the hardware part of your everything remote. Take your bottom shell with your PCB and gently push the clips into place while holding the whole thing at an angle. This makes it a little bit easier for the clips to flex out of the way. Close the shell like a book, ensuring the clips are properly seated. Insert your 2 M2x10 screws and tighten them down while holding the shell firmly closed. And that's it. Your everything remote is ready to have ESPHome installed. If you did it right, all your buttons should be the right way up and in the right place. Unfortunately, I did not. So here's one I prepared earlier. And that's it. Your everything remote is ready to have ESPHome installed and for you to write your very own YAML. Before we can start uploading code or using the remote in Home Assistant, we need to add it as a new ESPHome device. ESPHome's like our operating system, similar to how you might think about Windows. We need to get our microcontroller set up as an ESPHome device before we can do anything else. The good news? Home Assistant makes this really easy, even if it's your first time using ESPHome. Step 1 is you need to make sure ESPHome is installed. In Home Assistant, head to Settings, then Add-ons, and then click Add-on Store. Then you want to search for ESPHome Device Builder. There it is. I already have it installed, so this might look a little bit different. And you just want to get this all installed. Once it's installed, make sure you enable Start on Boot. And I like to turn on Show in Sidebar so I can easily find it a bit later. Once it's installed, you'll get ESPHome Builder on the left-hand side here. That'll look a bit like this. You obviously won't have any devices in there yet. Now we'll need to add a new device. We'll open the ESPHome Builder. You could click Add New Device down here and go through that process. That works perfectly fine, but I've found another process a little bit more reliable. Go to web.esphome.io and you'll be greeted with this page. This I found is the easiest way to set up a new ESPHome device. We want to click Connect, and you'll see this window pop up if you're using Chrome or a Chromium browser. Then you want to plug your USB cable into your device. You can see we had a new device pop up here, USB serial COM4. So we want to select that device and hit Connect. Now we have an option to prepare for first use. So if we click this button and hit Install, it's going to install a basic version of ESPHome on our microcontroller, which will allow us to access it in the Home Assistant device builder and work on a YAML over there. And we'll just wait for this install process to finish. Okay, our configuration's been installed. Just hit close. And now we'll connect it to Wi-Fi. In my case, I'm going to select my Wi-Fi and enter my password. And hit connect. And there we go. We're all done. Once your device is provisioned, you can head back to Home Assistant and open your ESP Home Builder. You should see this banner at the top that says Discovered One Device. We're going to hit Show, and we can see our new device in the top here. We want to press Take Control. This just means you're sort of making it part of your ESP Home configuration, and we're going to give it a name. In this case, we're going to call it the Everything Remote. Then we'll hit Take Control. To finish taking control of the Everything Remote, the new configuration needs to be installed on this device. So it's just asking that we install a new config after the one we did before. So we're going to hit Install, and there we go. The really nice thing about ESP Home is after we've done that initial config and got everything set up and connected to our network, the really nice thing about ESP Home is once we've done the initial config with the cable, we can update it over the air or via Wi-Fi from that point on. So like before, we'll just wait a couple minutes for this to finish installing. And there we are. This name here, ESP Home Web, etc., has been assigned by the ESPHome web installer. So it's a good idea, though I've been a bit lazy and haven't changed the rest of these, it's a good idea to rename your host name. In this case, I'm going to call it Everything Remote 01. Okay, we'll hit rename. And when we see this success message down the bottom here, we can safely close the window. And we can see that it's been renamed to Everything Remote 01. Now, before we get any further, we're just going to add this device to Home Assistant. So let's go over to our settings, then our devices, go to ESP Home, and then you should see a new device discovered, Everything Remote. We'll hit Add. Now it'll be added in as a device in Home Assistant. We'll assign it a room or an area, in this case living room, and hit Finish. Now we can see it in here, Everything Remote. Now obviously at the moment all this is a dumb ESP32. It doesn't have any code on it aside from the ESP Home code, so there are no entities exposed. And so there's no entities exposed. What we need to do now is go back to our ESP Home Builder and open up the YAML for our Everything Remote by clicking the Edit button here. Now before we start wiring up buttons and getting things set up, let's take a step back. If you've never used ESP Home before, this YAML config file might look a little intimidating at first, so let's break it down. When you create a new device in ESP Home, regardless of which method you use, you'll get a blank config file that looks something like this. Before we go any further, I'll take you through this so that you can understand a bit of what's happening. First of all, we have the ESP Home block. This just defines the name of our device and a couple of other minor details. So we can see here, name. That's the name we just set up, or the host name. Then we have our friendly name, which in this case is Everything Remote. That's what will be used in Home Assistant. Then we have our version of ESP Home and whether we want to add a MAC address suffix to this one. In this case, we just leave that on false. Next down the line, we have the ESP32 block. The ESP32 at the top just says this is an ESP32 board. There are other ESP boards, but in this case, that's what we're using. Under that, we have the board. This would be the type of board. In our case, it's just a dev board, which is what you'll use most of the time with these DIY projects. Then we have framework and the type of framework. In this case, by default, it's ESPIDF. Now we have the logger line and the API line. Each of these enables some functionality just by being here. So logger enables logging so you can see debug messages while testing. Including this just tells the ESP to make sure it's enabled when we install the software. To save battery life later, we'll remove this piece of code or comment it out. If you're not familiar with that term, commenting out just means that you turn a piece of code into a comment, like this green line here, by, in the case of YAML, adding a hash in front of the line. This just tells our software to ignore this line. Below that, we have API. This enables the Home Assistant API. Like Logger, this just makes sure the API is enabled when we install our software. OTA stands for over-the-air updates, so you can upload new code without plugging in. And then the platform is just the method through which we're doing that, which in our case is ESPHome. Then we have Wi-Fi, which we've already had to set up once. So this is our SSID and our password. It's pretty self-explanatory. This is just the Wi-Fi network that the device is connecting to. Your YAML might include some slightly different lines. That's totally fine. Just make sure that the board type is correct and that the Wi-Fi details are corrected. That's the skeleton of pretty much every ESPHome project. Once you've got this in place, you can start adding sensors, buttons, and other features underneath. Consider this your settings section. Now we'll start working on our YAML. First of all, because this is a battery-powered device, we want to keep power consumption low, but we also want it to wake up instantly and feel responsive. That's where light sleep comes in. If you're familiar with deep sleep in ESPHome, you'll know that it puts the ESP32 into a full shutdown, which is really good for saving power, but not so great for response times. It has to reboot, essentially, each time it wakes up. Light sleep, on the other hand, is kind of a sweet spot for this project. It pauses the processor and peripherals, keeps the Wi-Fi connection and memory intact, and will wake instantly from any GPIO pin, including every button on the remote. So we get better battery life and the remote can feel really snappy. To turn on light sleep, we just need to add one line inside our Wi-Fi section. So underneath my password, I'm going to put in power_save_mode, then a colon, and in all caps, light. That's it. Now ESPHome will put the chip into light sleep whenever it's idle, like when you're not pressing buttons, and it'll wake up instantly the moment any GPIO input changes. From here, we'll wire up one of those buttons and show how to detect both single and long presses, and thanks to light sleep, they'll register instantly whenever you use the remote. We're going to start by programming a single button. I'll walk you through it step by step. First, we'll set it up to detect regular presses, test that in Home Assistant, and then we'll expand it to support long presses too. Let's start by adding a basic binary sensor to our YAML. A binary sensor is just what it sounds like. It can be on or off, true or false, or in our case, pressed or not pressed. Perfect for a button, which can only be one of those things. This example will detect a short press, like a quick tap, and send a custom event into Home Assistant so we can use it in automations. Here's what that looks like. We'll work through it line by line together so that you can understand what each section does. First, we have binary sensor. This is just defining the start of a list of binary sensors. Then we have platform, in this case GPIO. This just tells ESPHome that the sensor is connected to a physical pin. Then we have pin, where we're going to configure how the pin behaves. So first is number. This is the pin number we're using. In this case, we're going to use GPIO 22, which is what the select button is connected to. Then we have the mode section, which lets us manually define how the pin works. So first we have input, true. This is just forcing the pin to act as an input. Then we have pull up, true, which is enabling that internal pull up resistor we talked about in the electronics part of the project. Then under the mode section, we want to invert the logic. So in this case, because we're using a pull up resistor and the button connects the pin to ground, we flip the logic so it'll read as pressed or true when it's pulled low. Now you only need to use the pull-up resistors for GPIOs that don't have external resistors. Pins 34 and 35 already have pull-up resistors on the board. We soldered those on earlier. So for those, you can just omit the pull-up line. Now we have name. This is just a friendly name you'll see in the logs. It can be anything, but something meaningful is usually good. Just something you'll remember. In my case, I've just named them after whatever button they're connected to. Then ID. This is the internal ID we can use later if we want to refer to this button elsewhere in the configuration. It's a really good idea to get in the habit of giving all of these sensors an ID. Now you can't just use select for the ID, that'll break the compiler. So in my case, I've just used select_button. For the others, I've just used their function like left, right, up, down, etc. Then we have internal. In this case, we've set it to true. This will hide the sensor from your Home Assistant dashboard, so it won't show up as an entity, but it still works perfectly behind the scenes for automations. I have my shortcut and brightness buttons set to false, so I can use them in automations a little more easily. Then we're using on multi-click. This is where we tell ESPHome what to do when the button's pressed. You can define multiple press types here. We're starting with just a single click. Under timing, we're saying for any time the button is on for at most 350 milliseconds, then send a Home Assistant event. This will send a custom event into Home Assistant that we can later use for our automations. There's actually a slight mistake here, and you can see because it's being highlighted. The event can be called whatever we'd like, but it needs to start with ESPHome, then a dot, and then your own name. In our case, we've just gone with remote button pressed. And then under the data section, we just define what data we're sending when the button is pressed. So in our case, we want to include that it's the select button that's being pressed, and we want to include a press type so that when we add long press functionality later, we're able to tell which is which. You'll see what a long press version of this looks like later, but in theory, you could do double tap, triple tap, whatever you'd like, just by changing this timing and sending a different message to Home Assistant. So what does this actually all do? Well, it watches GPIO 22 for a button press. If that press is less than 350 milliseconds, it'll send a custom event called ESPHome.remote_button_pressed, and that'll contain the data select_button and single for type. Now, you might notice that indents are used quite a lot in YAML. Different sections are indented different amounts. The indents are used to help tell our compiler what each set of parameters belongs to. I refer to each of these sections as blocks. So if I said our binary sensor block, we'd be referring to this whole section. If I said our pin block, I'd be referring to just this section. If you've never written YAML before, just think of it as a recipe. Each indentation tells ESPHome what ingredient belongs to what step. Once you've gotten this far, you can save your code by clicking Save in the top right, and then install it by clicking Install. You get a few options for how to install it, but because we set up OTA, or over-the-air updates, we can click wirelessly. And now, just like before, it'll compile our code and send it off to our ESP32. If it runs into any problems, it'll display an error message here. You can compare your code to my YAML in the blog post to try and figure out where you might have made a mistake. When you see this OTA successfully uploaded program, you're all done. We can hit stop. And now we need to test our code. To do that, we just open our developer tools in Home Assistant. Go to Events. And in our Listen to Events, we want to type the event type we created in our YAML. So in our case, that was ESPHome dot remote underscore button underscore pressed. Click Start Listening and then press the button on your remote. You should see all the information we included in the data section. In our case, the button is the select button and the type is a single press. There's some extra information here as well. This is what the remote's sending to Home Assistant when we push a button, and it's what we'll use to trigger automations, like playing a movie, toggling lights, or launching Plex. We're doing it this way because it gives us total control. Short presses, long presses, custom actions, and no extra devices in your UI unless you want them. If there were an entity exposed for every button on the remote, it would quickly get cluttered in Home Assistant. Now let's upgrade our YAML to handle long presses as well, like holding the button down for half a second or more. Now we'll go back to the ESP Home Builder, hit Edit on our remote, and add some more YAML below the first section. We don't need to add another binary sensor. What we're going to do instead is add another timing section in the On Multi-Click block. The easiest way to do this is just to copy paste our previous timing section. So we'll hit Control-C and then paste in our new section, making sure that the indents all match the previous timing section. Okay, now we just need to change what timing constitutes a long press. So we're going to change this to on for at least 500 milliseconds. What that means is if the button is held for at least 500 milliseconds, it'll continue to this section of the YAML. So now we can't be sending the same message to indicate a single and a long press. So we're going to change the type in this second block to long. Just like with the short press, we're sending a custom event into Home Assistant. It uses the same event name, so we can keep all the button presses in a single automation if we'd like to. This tells Home Assistant which button was pressed and that it was a long type press. We can use this to trigger entirely different automations from the short press, for example. So now if we look at this whole On Multi-Click section, if the button is on for at most 350 milliseconds, then we'll send a custom event with button select button and type single. But if the button is on for at least 500 milliseconds, then we'll send a custom event with the same button of select button, but the type long. Anything in between that 350 milliseconds and 500 milliseconds will be ignored, so we don't get any accidental duplicate actions. Now we're going to save our code again in the top right. We're going to compile and install by clicking Install and then wirelessly. Once this is finished installing, we can test our new code. When you see this purple text, you're all good. Just like before, we'll go into Developer Tools, then Events, and in Listen to Events, we type ESPHome.remote_button_pressed and hit Start Listening. Now, when we tap our select button, we should see the same message as last time. But when we hold it, we see long instead of single in our event. Once that's confirmed working, you're all set to repeat the pattern for any other buttons you want. Now, in this case, we've used a binary sensor with on multi-click, which is perfect for button inputs. But ESPHome supports lots of other sensors and input types. Some useful ones are sensor for numeric values like temperature, signal strength, or battery voltage, switch for toggling outputs on or off, text sensor for status strings like Wi-Fi info, button for one-time actions like restarting a device, and then number and select for UI controls in Home Assistant. If you want to learn more, the ESPHome documentation is genuinely excellent, with lots of examples and explanations that are super helpful, especially if you're new to all this. We're not going to go through all 21 buttons here. It's the same setup every time, just change the pin number, the button name and the ID, and then your message that gets sent to ESPHome. Remember that pins 34 and 35 already have a pull-up resistor and don't need the internal pull-up activated. It'll throw an error if you accidentally leave it in there. There's a table on the blog post that shows you which pins are connected to which buttons, so it's a little easier to write the rest of your YAML. Remember, if this all seems a bit much or you'd like to skip through it for now and come back to understanding it later, you can borrow my YAML in the blog post over on the Stockpot website. From here, you can use these events to power any kind of automation you like. Lights, media controls, scenes, scripts, you name it. Couple of extra notes. You can't name a button select because it's a reserved keyword in ESPHome. It'll break the compiler and throw an error, which is why I named it select_button instead, but the rest are called left, right, up, down, etc. Now, one thing you may encounter as you add more buttons to your YAML is that your code will stop working after a reboot. This took me a while to troubleshoot when I was working on mine, but it turns out the ESP IDF framework is not very good at handling a large number of sensors. The good news is it's a really easy fix. You just need to change your framework to Arduino instead of ESP. Once you've got all your buttons set up in YAML, install your new code and test them all out one by one. If it's all working, you've successfully programmed an ESPHome device. If not, just compare it to my YAML on the site to see what you missed. At this point, you've connected your ESP32 to Wi-Fi, flashed your first ESPHome config, set up button presses and custom events, and verified everything in Home Assistant. That's a massive win, especially if this is your first microcontroller or ESPHome project. Let's put those buttons to work. Next up is the automations. This is the fun bit. We'll take our new Home Assistant inputs and control some outputs with them. Just like with the soldering and the programming, I'll show you how to do some basic automations and make sure you have the tools to do the rest yourself. Let's start with controlling a light's brightness. For this kind of automation, you might find it much easier to expose the relevant buttons in our Home Assistant interface by setting them to internal false in the ESPHome YAML. That's what I've done for pin 26 and 27 in my ESPHome config. This allows me to see them here in Home Assistant when I open up my Everything remote device. If you've already made some simple automations in Home Assistant, you probably already know you could use this to power automations of all kinds. However, this doesn't provide access to our long event for when we hold down a button or to any of the buttons we have hidden in our ESPHome YAML, or for any of the buttons we have set to internal in our ESPHome YAML. Instead, what I'm going to do is show you how to trigger automations based on events. This can be a really powerful way to create automations and oddly enough makes some things a lot easier to understand as your automations get more complex. First, we need to set our trigger. In our case, we want to trigger our automation when the brightness up and brightness down buttons are pressed. If you remember back to our ESPHome YAML, we send an event called ESPHome.remote_button_pressed whenever a button is pressed. So we're going to set that as our trigger. Click Add Trigger, search for Event, and choose Manual Event. Now we just need to type ESPHome dot remote underscore button underscore pressed. Now this automation will be triggered whenever ESP remote button pressed event is fired, as you can see here. For now, because we want to capture all the button presses, we're going to leave event data empty. Great. Now we need to choose what action we perform based on the data that event is carrying. We can do this by adding a building block to our then do section. Building blocks let us add additional logic to our automation. In our case, we're going to use a choose block to choose what we're going to do based on a condition. We can add as many options as we want to this choose block, so we could use it for all 21 buttons or 42 functions available on our remote with the short and long presses. And we don't need a separate automation for each one. First, we need our condition. We'll set up our brightness up control first. To do this, we need to add a value template to our conditions in option 1. Click Add Condition, then search for Template. And then we're going to type in the value template section. Then we're going to add 2 braces and type trigger.event.data.button, then 2 equal signs, and brightness up in quotes. Now all this is saying is if the trigger.event.data.button is exactly equal to brightness up, then the result of this template is true. A value template is really just a little code block. We can type code that evaluates as true or false and use it to determine whether we complete the action tied to that option. And because we want to check both these conditions, we write the word and then trigger.event.data.type, 2 equal signs, and in quotes single, and then 2 braces to close it off. What this means is that this template will only be true if the trigger.event.data.button is brightness up and the trigger.event.data.type is single. The brightness up button has been pressed once. If we changed this single to long, it would trigger with a long press. Now we need to choose an action that will happen when those conditions are met. Now in my case, I'm just controlling a lamp. So I'm going to go to Device, then I'm going to select bedside lamp Dylan, that's my bedside lamp. And I'm going to increase brightness. And there we go. That's our first option. Now we'll save our automation. I'm going to call it remote lamp. And I really would recommend including a description for all of your automations. It makes it a lot easier to remember what they were for when you need to conduct maintenance down the track. Now we'll save the new name. Now we can test that. And it looks like it's working. Now we just need to add our other options. Obviously, the next step is a brightness down button. So let's duplicate our option and change the condition. Now we want this to trigger with the brightness down button, not the brightness up button. So we can just change that inside our value template. And then we need to change the action. We'll set it to decrease bedside lamp brightness. Simple as that. Now I'll save this and let's test that out. And that's working perfectly. Now I want to have a long press on brightness up, increase the brightness to 100%, and the opposite for the brightness down button. So we'll do the same thing, but change the trigger event data type section to long, so it's true with a long press. So let's duplicate our first option here. Remember that was for brightness up. And now we want this condition to be true with a long press. And in the case of a long press, we want it to turn on the bedside lamp with the brightness set to 100. And now let's do that again, but for the off option. So brightness down, and data type is going to be long. And we're going to set it to turn off bedside lamp. And now we'll save that option. And now we'll save that automation and test it out. That one's working too. Perfect. So now you've created an event-based trigger. You've used a choose block to handle multiple button presses. You've added logic to differentiate short and long presses. And we've set it up to control a lamp. There you go. That's how to use the events your new remote is sending to drive automations. Now, technically, in the background, all of these automations are also just YAML. If you click the three dots at the top and select Edit in YAML, you can see the underlying code running your automation. This is a great way to learn more. You can use the UI to create an automation, then see under the hood by looking at the YAML. You should have everything you need to dive into creating your own automations now. If you're looking to control your Samsung TV, like in the video, I've included the YAML for that automation in the blog post on my site. It's a little too complex for the scope of this tutorial, but you might find it interesting nonetheless. A quick note, a recent change to Samsung's APIs have broken some parts of it, so you might need to do some troubleshooting yourself. Enjoy your new remote. If you've followed this entire tutorial from start to finish, well done, congratulations. I hope you've learned a lot along the way. Please leave a like and a comment to help the algorithm. Longer form tutorials like this don't usually perform very well on YouTube, so every little bit helps. If you enjoyed this, I'll consider doing some more tutorial style projects down the line, perhaps a touch more advanced than this. I've got some ideas for more smart home oriented projects, but also some more fun little silly side projects. I look forward to sharing the next one with you. If you're not already, subscribe to see what else I get up to. Catch you next time.